Hello, Strat students. In this lecture, we're going to briefly be covering the difference between confined and unconfined flow and how we might tell them apart in the sedimentary record. The difference between a confined or channelized flow and an unconfined flow may seem very simple when we just observe them in our backyard, but when we try to differentiate between these two different types of flow in the rock record, it can actually be really tricky. Sometimes we're lucky enough that a beautiful channel body or some other clearly identifying feature is exposed. But more often than not, we're just not that lucky. Instead, we have to depend on careful observations, our knowledge of these types of environments and different types of flow, and a little bit of logical reasoning to put it all together. Confined flow or channelized flow is simply where the flow of a fluid is limited or bounded on all sides by some sort of barrier. This results in the flow within the channel being parallel to the channel orientation. In an unconfined flow, there are no lateral boundaries or barriers to flow. This means that the fluid can spread out or have a current in any direction it very well pleases. The idea or concepts of confined and unconfined flow are going to be very important to a number of depositional environments we'll discuss in this class. But it's easiest to think about them at first in the context of fluvial or river and deltaic systems, which happen to be the topics of this week's lectures. So, for the rest of this particular discussion, we'll be thinking about confined flow as river channels and unconfined flow as deltas. In this really nice Google Earth image of the Missouri River just south of Williston, North Dakota, you can see a great example of where a meandering fluvial system enters a reservoir and starts to build a delta. But we hardly ever get that bird's eye view of a fluvial deltaic or any other sedimentary system in the rock record. Instead, we have to infer confined and unconfined flow from things that we can see in a rock. This brings us back to our fundamental observations in sedimentary geology. In order to figure out whether a system is confined or unconfined, we're going to have to take a look at said structures, at grain size, at the geometry of bedding, and the relationships between our beds and bed sets. As we watch this small, homemade fluvial deltaic system evolve through time, we're going to think about what changes in grain size and said structures, if any, we might observe in the confined and unconfined portions of this system. As we compare and contrast these confined and unconfined systems, we're going to need to look for clues that help us differentiate between the two. One of the first things you should always look at when trying to infer the nature of a sedimentary deposit are its contacts. The upper, lower, and lateral contacts of a sedimentary deposit, whether sharp, gradational, or erosional, are how we put that deposit in context. Confined or channelized flow always has an erosive, basal, or lower contact. And while there may be sharp or gradational contacts within a channel deposit, the lateral contacts between a channel deposit and whatever it's cutting into will also be erosional. On the other hand, basal and lateral contacts of unconfined flow deposits will likely be sharp or gradational. While contacts are essential for us to understand the position of a particular sedimentary deposit within the landscape, they don't give us the whole story. We also have to take careful note of sediment texture and sedimentary structures within a deposit, not just in one spot, but how they change laterally and vertically or through time. The reason taking a look at sedimentary structures and sedimentary textures are so essential are because they are the two things that can tell us about the change in energy within a system. As you watch our little bucket fluvial deltaic system evolve, note two things. First, that the velocity or discharge or energy within the channel is relatively constant. And the second thing to note is that once you enter unconfined flow, or the deltaic portion of our little system, energy is not constant, velocity is not constant, and as you follow the flow in the direction of flow, the amount of energy in the system will ultimately decrease. So if you're taking a look at a sedimentary body that's a channel, you can expect the grain size and sedimentary structures within that channel to be relatively consistent or constant. If you are in an unconfined system, however, you can expect grain size and sedimentary structures to change in the direction of flow. In an unconfined flow, grain size will gradually decrease as velocity of the flow decreases and larger material is dropped out of the load. As energy decreases, you will also see said structures that reflect lower and lower velocities. Since sediment supply and energy both decrease in the direction of flow within an unconfined system, you will also see that sedimentary bodies created by unconfined flow will thin in the direction of flow. In sedimentary units that accumulate in channels, however, the thickness of the unit will be relatively constant in the direction of flow. For the last little portion of this video, we're going to walk through an example created by my supervisor and the original creator of this content, John Isbell, at the University of Wisconsin-Milwaukee. I'm also going to be replaying the little box model video we just watched so that you can keep that system in mind as we take a look at a similar set of systems in our vertical or third dimension. In the figure above, you see the approximation of an outcrop on the lower left with 5 different sand bodies, and on the right you see sedimentary logs, section 1 and section 2, that log their way through each of those sand bodies. The yellow colors in the outcrop sketch and in the sedimentary logs indicate sand-sized material, while the gray and white colors with the hash marks in both the sedimentary logs and the outcrop represent fine-grained material, either silt or clay. The goal of this exercise is to try to determine whether each of these 5 sand bodies were created by confined or unconfined flow. In addition to looking at the stacking patterns, the geometry of these sand bodies, and changes in said textures through the vertical sections, we're also going to be looking at flow directions. So as we often do in sedimentary geology, we're going to start at the bottom and go to the top. Sand body B has a sharp lower contact and an erosional upper contact, and we're not able to see its lateral contacts within the context of this outcrop, so we're not able to consider those when trying to interpret this particular deposit. We can see in the sedimentary logs to the right that in section 1 and section 2, sand body B is coarsening upward, and you have relatively high energy sedimentary structures throughout the entire deposit. The final information we have available to us on sedimentary body B, or sand body B, is its flow directions and the dip of its bounding surfaces. The true sort of compass rose direction doesn't really matter to us right now. We more want to look at the distribution of flow direction, so how spread out are they, and how do they relate to the orientation or dip of that bounding surface. So in both section 1 and section 2, the flow directions in sand body B are between 180 degrees and 230 degrees. So they have approximately 50 degrees of spread. That spread is centered around, right, like 210 degrees, which happens to be the orientation of the dip of the bounding surface. So we can say that the flow directions in sand body B roughly parallel the dip of the bounding surface. This is a phenomenon that we call downstream accretion, which is something we'll talk about more next week. But mostly what it means is that the sand is accumulating in the direction of flow. So as you're building the sand body, you're adding sand, or you're depositing sand in the direction of flow, downstream accretion. To summarize sand body B, we can say we have a sand body with kind of a sheet-like geometry or a relatively constant thickness in this outcrop. It's coarsening upward and has a sharp lower contact and is being deposited through downstream accretion. And that we have relatively consistent or high flow velocities, as we can see from our asymmetrical ripples and 3D crossbeds. Largely because of the sharp lower or basal contact, we're going to be interpreting sand body B as the result of deposition through an unconfined flow. The coarsening upward package within sand body B and the downstream accretion of the sediments indicate to us also that sand body B is likely the foreset part of a delta system. And hopefully why that is will become more apparent as you watch the delta portion of this week's lecture videos. All right, we're going to move a little bit quicker through the next couple. On the outcrop picture, or the outcrop scale, sand body A seems to be pretty similar to sand body B, but when you zoom in, they actually look quite a bit different. Sand body A has a erosional lower contact or basal contact and a sharp upper contact, and we can't see what's going on laterally. If we take a look over at sections 1 and section 2, we see two kind of different patterns going through sand body A. In section 2, the whole of body A is composed of sand, and we have a fining upward sequence, again with an erosional contact and pretty high energy bed forms throughout the entire sand body. If we take a look at section 1, the base of the section looks very similar to section 2, but the rest of that, the thickness of that sand body is filled in by some clay and silt, so a shale deposit. The contact between the fine-grained material that's part of sand body A and the coarse-grained material is sharp. This to us means that the amount of energy in the system changed very abruptly from relatively high to relatively low. If we take a look at the flow directions in sections 1 and section 2 for sand body A, which we can see by the brackets are just from the sand portion and not from the shale portion, the range in flow directions in this unit is between 210 degrees and 230 degrees. So just a 20-degree spread, which is quite a bit tighter than our sand body B. We can also see that in sand body A, the dip of the bounding surface is not the strike of the bounding surface, but the dip direction of the bounding surface is at 130 degrees, or oriented towards 130 degrees. That is directly perpendicular to the average flow directions indicated by the sedimentary structures in the sand body. This indicates to us that sediment is accumulating or accreting in a direction that is perpendicular to the flow of the fluid. This is representative of a phenomenon known as lateral accretion, which again we'll talk about more next week. Put all together, these characteristics of sand body A, and especially the erosional base of the sand body, indicate that it was formed through deposition in a channelized or confined sedimentary environment. The plug of fine-grained materials that we see in sand body A that's measured through in section 1 is also indicative of a fluvial or channelized setting, which you'll learn more about in other parts of this week's lectures. To finish off, we're going to talk through the upper three sand bodies kind of together as they represent different parts of similar unconfined flow systems. The basal contacts for each of these three sand bodies ranges from sharp to lightly erosional. Each body is fining upward and has sedimentary structures ranging from 3D dunes to current ripples to upper plane beds that indicate relatively high flow velocities. But the thing to key into here is to take a look at the flow directions, the range of flow directions, and then take a look at the upper left-hand corner of the picture where we have cardinal directions indicated for the outcrop picture. The flow direction in each of these sand bodies is more or less towards the west, remembering that 270 degrees is the same as due west. And also note that the two uppermost sand bodies both thin towards the west. So for the upper two sand bodies, we have sharp lower contacts with flow directions, with thinning of the sand body in the direction of flow, both hallmarks of unconfined flow. Each of these upper three sand bodies represents a different sort of part of an unconfined flow system. The lowermost sand body probably represents some sort of proximal unconfined flow position where you still have relatively high energy, you have some traction, so you're able to create a small erosional surface, though nothing major like you see below sand body A. And then in the upper two sand bodies, you're getting more and more distal from your the source of the unconfined flow. That concludes our introduction to the concepts of confined and unconfined flow. Please try to keep these ideas in mind as you learn more about fluvial and deltaic systems for the rest of the lecture this week. And do remember that the concepts of confined and unconfined flow can be applied to any sedimentary environment where there's a fluid, so transporting sediment. So basically everything. That includes glaciers like you see here, but other sediment transport processes to keep in mind, or settings to keep in mind, include alluvial fans, which is something you'll see in lab this week, but also debris flows can behave like this. And you can also create channels in subaqueous settings. All right, that about wraps it up. Please let me know if you have any questions, and stay healthy and stay safe.